All right, welcome to Chapter 11. Chapter 11 is mostly about polynomials, so let's just get right into it, I suppose. Number one, let's clear the sauces from last time. Number one, we have negative 7c squared plus 5c plus 3. Okay, so basically, I'll make up another problem again that's similar to this, and I'll just kind of talk you through what you should be doing. So let's take, I don't know, say 9. I'll just use x instead of c, but it's the same thing essentially. Plus 3x plus 2. And then we'll add this with, say, negative 4 x squared, I almost wrote c, minus 3x plus 1. Okay, so all you're doing when you're adding these polynomials, you can clearly see the plus sign in between these things. That means we're going to add the polynomials. Now to do that, we just add the like terms. It's it. So find the like terms and put them together. So the like terms that we can find are 9x squared and negative 4x squared. So we're going to combine these because they're both x squared terms. Now this is a 9 plus a negative 4. And a 9 plus a negative 4 is the same thing as just 9 minus 4, which makes that 5. That's 5x squared. And then we also look for some more like terms. We got some more like terms. We got the x terms. We got 3x, and then we have negative 3x. So we have 3x plus negative 3x. So that's 3 plus negative 3, which again is the same thing as just 3 minus 3, which actually makes 0x. So when these come together, they cancel out, and it's not going to be an x term. So I'll write 0x for now, but in the final answer, it won't be there. Okay, but yeah, it's just the same combined like terms. And then lastly, we have 2 and 1. These are just the constants. We have a positive 2 plus a positive 1. 2 plus 1 makes a positive 3. So there's our answer. Our final answer being 5x squared plus, plus 3. Since again, 0x is like not a thing. So number 2. Let's do number 2 as well. Actually, I'll use the same problem to explain number 2, except I'll make it a subtraction problem. So let's clear this. I don't want to rewrite another problem. We could just use the same polynomial to explain it. So it's going to be a minus problem now. So it's a little different, but not too different. Now, when it comes to a minus problem, a subtraction problem like this, you're subtracting all of these terms. So in a sense, you're subtracting a negative 4x squared. You're subtracting a negative 3x, and you're subtracting a positive 1, which I ran out of screen for. But that's what you're doing. You're subtracting all 3 of these. So in essence, when you do that, for example, well, I should have just kept that. When you subtract a negative 4x squared, right, because I'm subtracting that term, a negative 4x squared, that's going to make that a positive 4x squared. When I subtract a negative 3x, subtracting a negative 3x, subtracting a negative again makes that a positive. So it's going to make that plus 3x. And then when I'm subtracting a positive 1, I'm just subtracting a 1. So it's just going to be minus 1. So what I tend to do is just distribute the negative. And that's pretty much what I just did. A negative 1 times a negative 4 makes that a positive 4. A negative times a negative 3 makes it a positive 3. And a negative times a positive 1 makes a negative 1. So I now think of this as just an adding problem, where I'm just going to take the like terms and combine them again. But I do like to rewrite these terms so I don't get too confused. So now let's combine our like terms. We have 9x squared plus 4x squared. Because remember, subtracting a negative makes this a plus now. So 9x squared plus 4x squared is going to be 9 plus 4 is 13. So 13x squared. That's for those. Then we have our x terms. We got 3x and we have plus 3x. Because remember, it's plus 3x now because subtracting a negative 3 makes that plus 3. So 3x plus 3x makes 6x. And what else we got? We got the 2 and the 1. So it is a subtracting 1, right? Because it's subtracting a positive 1, which means minus 1. So 2 minus 1 is 1. So it's a positive 1. It's plus 1. So there's your final answer. 13x squared plus 6x plus 1. All right, so your problems are very similar to that. Number 3 is very similar to that. Number 4 is a little different. Let's talk about number 4. So number 4, we have, I'm going to say, I'll make a different one. Negative x squared in my problem. I'll say negative 2x plus 9 or something. So all we're going to do here is just distribute. We're just multiplying. So when I take a negative x squared times negative 2x, this is a negative 1 times a negative 2, which makes it positive 2 to begin with. And then when I combine these x's together, an x squared times an x makes an x to the third. Because when you're multiplying x's, x squared times x, you're actually just kind of adding how many there are. So you have 2x's here and x here, which makes together 3 of them, right? Because x squared is x times x. And then you're multiplying another x to it. So you're just multiplying 3x's, makes it x to the third. So that's 2x to the third. And then when I distribute to the second term, I've got a negative times a positive 9. That negative times a positive 9 turns into a negative 9. And this x squared carries with the term. It doesn't build, it doesn't get any larger because there's no x's here to combine with. It just stays as x squared. And that's it. That's the answer. Let's talk about something like number 5. Number 5, let me make another problem. Let's say I have 2x y to the 5th minus 4x squared y squared. I'm going to make it slightly different than the one you have. And then plus 7, we'll say x to the third y. Okay, all divided by xy. So what this is doing is we're dividing every term by xy. We're going to divide this term by xy. We're going to divide the middle term by xy. We're going to divide this last term by xy. So we're dividing everything individually by xy. So let's focus our attention here in the front first. If I do 2x, I'll write it over here, 2x y to the 5th divided by xy, well, we're just kind of canceling things out. So an x on top and an x on bottom, those x's will just straight up cancel out. And then this y will take out one of the y's on the top, making it just y to the 4th on top. So that essentially turns that term into just 2y to the 4th. Now let's talk about the second term. Now this is a negative 4, so I'm going to make sure that's included. So if we're going to do a negative 4, x squared y squared divided by xy, again, we're taking this x is going to cancel with one of these x's up here, making it just x to the 1st. And this y will cancel with one of the y's that is up here, making it y to the 1st. So you're taking a y away from it, because remember, all this means is 2 x's and 2 y's. When it says x squared, y squared, it just means you have 2 of them. And when you're taking one of them away, then it's just a single x and a single y. So that makes this just a negative 4 x, y. You can say x to the 1st, y to the 1st if you want to, but x, y is just the same thing. And then lastly, we'll do the last one here. So we're going to have 7x to the 3rd y, 7x to the 3rd y over xy. So again, we're taking an x and a y out of the term. So if I take an x and this cancels out with one of these, and it's going to become x squared. And this y will cancel with this y, leaving no y's remaining at all. And that final part just is a positive 7x squared. And that's it. So you're just basically taking an xy out of each term. Long story short. Number 6 is very similar, with the exception of you're going to have to divide by a number. So for example, when you have do the same thing for number 6, you're going to have 3 divided by 3, like in the first term. And the 3 divided by 3 turns into 1. So keep that in mind. And the 6 divided by 3 for the second term, the 6 divided by 3 will turn into 2. So that's just like normal division. It's pretty much the same as this problem, except for that added factor of dividing the numbers. Number 7, let's talk about number 7. So this is a complicated looking problem, but it's nothing different than what we did in the first couple problems. So we have, let's say, 3x, and then let's say x plus 2. And then we'll add 4x, and we'll have 2x squared. I'm just going to make one up again. Minus 4x plus 3. I don't know. All right. To put this all together, we just have to first distribute each group. So we're going to distribute the 3x into that group, and then we're going to distribute the 4x into this group. So this will become 3x squared plus 6x, and this one would become 4 times 2 make 8, and this will be x to the third. The second one would, so we got 4x times negative 4x would be, remember it's times, not, you're not adding those. Some people think that 4x, negative 4x would cancel, not if you're multiplying them. 4 times negative 4 is negative 16, and the x makes x squared. And then 4x times 3, 4x times 3 is 12x. So now all you're doing is just combining like terms. I'm going to start from the biggest exponent and work our way down. So the biggest exponent I see is 8x to the third. I don't see any other 8x to the thirds or any other x to the thirds. So that's going to be brought down as part of my answer. So I've taken care of that. Now let's look for x squareds. I've got 2x squareds. I've got 3x squared, and then I've got negative 16x squared. So combining those, I've got 3 minus 16. 3 minus 16 would be negative 13. So this will be negative 13x squared. So I've taken care of those terms. Now let's take care of the x terms. I got 6x plus 12x. And combining those, 6 plus 12 makes 18, so that's going to be 18x. And I've taken care of all the terms. This will be my final answer. So it's just distribute and then add your like terms together. Okay, what else we got? Number 8 is very similar, so I'll let you do number 8. Number 9 we're going to skip for now. Let's look at number 10. Number 10 is a good one. Number 10 we're going to get our calculator out for. So go to your calculator, go to your y equals, and graph your polynomial that's given. I'm going to graph a different one, but you can just plug in yours. So I'll make it similar though. Mine will be x, we'll say x to the x to the third. So x to the third. No, I'll just go ahead and graph the one that you have. It'll just make more sense. Minus 8x squared minus 3x plus 90. Minus 3x plus 90. So when I graph it, okay, I can see where it crosses the x-axis. Now, if you're not seeing what I'm seeing, make sure you adjust your window. If you hit window, you can set your x min, x max, and x scale, and y min, y max, and y scale. If you do that, you should be okay. So go back to the graph. Now the question's asking, is x equal negative 3 a root? And to make sure that answer is yes or no, if it's a root, then we would see our polynomial cross the x-axis at that place. So if negative 3 is a root, we're going to see the polynomial cross at negative 3. Hoping I could find a tool there. And if you look on the graph, it does cross at negative 3. So that means it is a root. Okay? So obviously now it's either C or D, which is yes. But is it yes because f of negative 3 is not equal to 0? Or is it yes because f of negative 3 is equal to 0? Well, if there's a point, negative 3, on the x-axis, then it's equal to 0 because it's negative 3, 0, right? That's the point. That's the ordered pair of that point. So basically C, the answer choice C doesn't make any sense. If it's a root, it would exist at 0. It would exist on the x-axis. What D is basically saying is that, yes, it's a root because negative 3 is on the x-axis. When it says equal to 0, it's essentially meaning it is on the x-axis. So it's got to be D for that reason. Technically, B and C, those answer choices don't actually make any sense. Because, for example, B, when it says no, it's not a root. If it's not a root, then it wouldn't be on the x-axis. And what B says, it says no, f of negative 3 is on the x-axis because it says it is equal to 0. And that doesn't make any sense because if it is on the x-axis, it would be a root. And it said no. So B and C don't make any sense in terms of just logic. But yeah, the answer is D because -3 is on the x-axis, which means it is equal to 0. That's what equal to 0 means. So number 11 is, again, very straightforward. I'll let you do it. You just have to go back to your y equals, graph that equation, and then look to see where it crosses the x-axis. So it's just, again, one that you can do as long as you got a graphing calculator. And 12 is the exact same thing. Now just make sure you choose the right pair of order points, because A and B are opposite of C and D. So just make sure you don't get those backwards. You should be okay. Number 13 is already graphed for you, so don't play any games with it. Just look at the graph, see where it crosses the x-axis on the graph, and pick the correct answer choice. Okay, number 14 is a good question. Let's see. Oh, this is a long chapter, by the way. Sorry for the video being so long, but let's talk about number 14. There's a few facts I want to mention. So how many distinct real solutions does this equation have? Okay, well, actually, I'll go ahead and say this anyway. You can graph it, but let me point out one thing real fast. So if I have, see how that problem is an x to the 5th problem? Like it's an x to the 5th polynomial because x to the 5th is the largest one. Because this is the largest, this tells us it has 5 roots. Okay, now the catch is it doesn't necessarily have 5 real roots. They might be some real and some imaginary, but it does have 5 roots. Now, that doesn't make the answer 5, because it says in the question, how many real solutions does it have? And I'll talk to you about that in a second. But I do want to at least express to you that whatever the degree of the polynomials is how many roots it has. However, you got to keep in mind that some of these roots might be real, some of them might be imaginary. So let's look at the let's look back at our calculator. Let's graph this function that was given to us, x to the 5th minus x to the 4th. Oops, not like that. Okay, let me just start over. Okay, x to the 5th minus x to the 4th plus 10x to the 3rd. Oh, I did it again. Oh my gosh. Okay, x to the 4th. All right. This is just a struggle bus here. If you want to just skip ahead a couple seconds, go for it. Be my guest. Oh, it was, yeah, okay. The next one's minus. Okay, I think I got it typed in correctly. So if we graph it, real, excuse my voice crack there. Real roots are gonna be. I woke up just a moment ago, so it's the morning. Real roots are where it crosses the x-axis. Now it looks like it only crosses once, but just to be sure, let's go ahead and zoom out just to make sure. So hit zoom. Zoom out is the third option, so we'll just click that. We'll hit enter. Okay, so yeah, it's only going to hit the x-axis that one place, which means it only has one real root. So when I go back and explain like this part here that I was talking about a second ago, it does have 5 roots, but it only has, of those 5, it's only got one real root, and the other 4 roots must be imaginary roots. Okay, so keep that in mind. Just because you see this exponent, it does tell you how many roots, but it doesn't necessarily tell you how many real roots. To find out how many real roots it has, you can just look at the graph and see where across the x-axis. Because where across the x-axis is, are those real roots. So the answer should be just 1 there. Okay, let's talk about number 15. So number 15 is just a visual one. So let's say you have a polynomial that has a range of y greater than or equal to 22. Which of these must the function? Which of these must the function have? Okay, jeez. All right, so imagine a graph. Imagine y equals 22 right here, right? And the polynomial has a range of greater than or equal to 22, which means our polynomial exists above, I don't know what it looks like necessarily, but I know it exists above y equals 22, something like that. Because the range is greater than or equal to 22, so it's going to be from negative 20 or positive 22 all the way on up, right? That's our range. So what does this tell us about our graph? Well, a relative maximum, a relative minimum, an absolute maximum, or an absolute minimum. Let me make a little bit of a better graph here, just to kind of explain what some of these mean, okay? But it could be something like this, because this graph that I just drew, you can see it doesn't go past the 22. It's from 22 and then on upwards. So this is a representative, sketch of what is described in number 15. So it doesn't have an absolute maximum, because this is going to continue to go up forever, because it's going from 22 on up forever. So it doesn't have a max, because it like I said, it goes up forever. So it's not going to be A or C. So it comes down to a minimum. Now, because this has a minimum, like right here, for example, at 22, right? At some point, it's going to be at 22. There's no point lower than that, right? 22 is the lowest point on the polynomial. There's nothing down here. So because that's the absolute lowest, that is the absolute minimum. Okay? So it has to have an absolute minimum, because it bottoms out at 22. If that makes any sense. Okay? Just to explain what some of the other things are, a relative minimum is not an absolute minimum, but a minimum somewhere in the curve. So for example, my sketch here, this right here would be a relative minimum, because it's a minimum kind of relative to this part of the graph. Whereas a relative maximum, this technically would be a relative maximum, right? But it doesn't have to have it, It doesn't have to have it, because my graph could just be like this. So it doesn't necessarily have to have that relative minimum or relative max, but no matter what, it's guaranteed to have an absolute minimum, because there has to be a bottom point at 22 no matter what. That's what the problem's saying to us. So has to have an absolute minimum. Doesn't necessarily have to have a relative min or an absolute or relative max or anything like that. So, all right, let's look at number 16. So what's the y-intercept of the graph? You could actually answer this without graphing it. So just think about it. Remember the y-intercept. So a y-intercept is where it crosses the y-axis, right? So it could, you could cross y-axis there. I could have a function that crosses the y-axis here, right? It could cross the y-axis anywhere. Now let me point out a few things. This point on the y-axis, let's say that that's the point, 0, 5. And let's say this is the point 0, -3. And maybe it crosses down here. Maybe it crosses here at 0, -6. Or maybe it crosses up here at 0, 8. Notice, no matter what, if it crosses the y-axis somewhere, the y is, of course, going to be different depending on where the y-axis is hit. However, no matter what, the x is always 0. So, without actually having to graph this, which you still can, and you're more than welcome to, you can actually figure this out if you imagine x being 0. So imagine you plug 0 into the function. 0 to the third power, minus 12 times 0 to the second power, minus 0 plus 12. If you put 0 into that function for x, pretty much everything's going to go away except for one number. And that last number will be the y-intercept, because that's what's left, right? If you plug 0 in, what are you going to get out? So imagine if you plug 0 into the function, what would you have? What would the equation equal? And using that, you could figure out what the y-intercept is without even having to graph it. So, but you have to kind of remember that when it says y-intercept, when something says y-intercept, it always means x being equal to 0. Because when x is 0, the y value can be anything, and that would be on this y-axis here. This is 0, this is 0, but at 8, 0 at 5, 0 at -3, 0 at -6. So, just remember that x is always 0 on the y-axis. That's the key to that problem. Number 17, what are the intervals of increase of the function graphs below? So I'll sketch a different graph, but I'll let you guys, I'll explain it in this process. So let's say I have a graph that's like, let me put some, okay, let's say here's a point, and then we're coming down. We're going to have a point here, and then we're going to go back up again. So let's say I've got this curve function, right? And I'm asking, where is it increasing? Question mark. Well, remember, you have to read a function from left to right. So when I read this function from left to right, I know there's an arrow pointing down here, but if I start from this side to the right side, this is going uphill, right? So technically, even though the arrow is going down because it's continuing in that direction, you would actually follow it left to right, which makes it an increasing line, right? An increasing slope, a positive slope, a left to right going upward slope. So right there in red is increasing. Now, in green, I'll put decreasing because here, from this point downwards, it's decreasing. You see that? Because from left to right, you're decreasing. So that green part is decreasing. And then it turns around again, and you go start increasing again. So when it's asking what intervals am I increasing on my graph, of course, my graph is different than your graph. Keep that in mind. My graph is increasing all over here in this space. It's not increasing here in the middle where that green is, but it's increasing everywhere to the right of this. And it's increasing everywhere on the left side here as well. So what is that interval? Well, if this goes on forever, then this is going from negative infinity all the way on forever, all the way up to, if this is -1, -2. So it's increasing all the way from negative infinity up until it gets to -2. So my interval would be like this, negative infinity all the way to -2. Because once it gets to -2, that's when it starts going down again, right? But let's talk about it starts increasing again. So it's increasing. Where does it start increasing? Right here at +1, right? This is 1, that's 2, that's 3. So here at 1, it turns around, started increasing again. So, and it increases forever. So it goes from 1, right, all the way to positive infinity, since it's going to continue forever, increasing. So that's how I would say my interval. Just reading the x-axis, just look at the x-axis, right? This part of the x-axis, it's increasing. And then between -2 and 1, it's decreasing. And then from 1 all the way up to back to infinity, it's increasing again. So this region of the graph is increasing. This region of the graph is decreasing. And then again, increasing here. So, but you have to look at the x-axis, not the y-axis for this. So the x-axis, it's from negative infinity all the way on the left, all the way to -2. And then on the x-axis, it's from +1 all the way up to positive infinity. All right, don't look at the y-axis. That's very deceiving. Sometimes people get the habit of doing that, and that's not the case here. All right, so number 18, which of these functions has an absolute maximum? Again, I apologize for this video being very, 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 very long, but it's actually quite an in-depth chapter. So I'll go ahead and tell you. Number 18, something you need to know, I might have mentioned this in a previous video, even functions versus odd functions. Even functions have same end behavior, meaning that either both ends go up or both ends go down. Think of a quadratic, for example. A quadratic, either both ends go up or both ends go down. An odd function has opposite end behavior, meaning one side's going to go down and the other side's going to go up. It could be left and right, or it could be like left down, right up, or it could be left up and right down, but something like that. So knowing this, anytime I see an odd function, like if I see an x to the 5th function or an x to the 3rd function, or even a x to the 7th or something, I know that that graph, because it's odd, will always have one side that goes down, one side that goes up, meaning it will stretch all the way down to all the way up. So it never has a minimum because it goes down forever, and it never has a maximum because it goes up forever. So if I'm looking for an absolute max or an absolute min, and number 18 is asking for an absolute max, an odd function won't have it, because an odd function will always go up forever and it will always go down forever. Whereas an even function, it could have an absolute max because both ends would have to go down. So at some point you'd have a top point or a max point. They could both go up as well. And if they both go up as well, there's got to be some place where it bottoms out at. So an even function will have a max or a min, whereas odd functions can't have absolute maxes or mins. So when I look at the answer choices, basically, I can narrow it down to just the even functions. The odd functions I can rule out. Now think about the even functions. Remember, a positive even function would go upwards, meaning it would have a minimum point, whereas a negative even function would go downwards, meaning it has a maximum point. So if you're looking for something with an absolute maximum, the only thing that can have an absolute maximum is an even function that opens downwards, and that is only happening if the even function is negative as well. So based on that, I'm pretty sure you can get the right answer. So number 19 is asking which of these has range of all real numbers. So a range of all real numbers, remember range is the y-axis, meaning it goes uses all the y-axis. It goes all the way up and it goes all the way down. And just like I was saying in the last bit of this video, that the only functions that go all the way up and all the way down would be odd functions. Odd functions, remember, one side's going to go down, one side's going to go up. It could be left goes down, right goes up, or it could be left goes up, right goes down. But either way, it's always going to go up on one side and down on the other. So odd functions would be the only thing that would use all the y-axis. Because an even function, remember, an even function has to turn around and go back again. So it'll bottom out somewhere and won't use all the y-axis, right? Or even an upside down one, a negative one. It would max up somewhere because it has to turn around and it wouldn't use all the y-axis. So an odd function is the only one that would use all the y-axis. And if you look, you can find the odd function in your answer choices. Okay, number 20 is pretty self-explanatory. If the multiplicity means that it occurs 2 times at 5 and 3 times at 8, and the multiplicity at 5 is even, and the multiplicity at 8 is odd because it happens an even number of times at 5 and an odd number of times at 8. Which of these statements accurately describes number 21, this graph? So what I see in the graph is because both ends are going down in that graph, both ends are going down in that graph, the one that you see, that would have to be an even function because remember, they go the same direction, both ends do. Both ends are going the same way. It has to be even. Now, since both ends are going down, I'll let you figure out whether that's an even function that's even or positive or an even function that's negative. But it definitely is even since the fact that both ends go down. But yeah, I'll just narrow it down for you in that sense. Okay, and the last one, 22. Basically, when it says, time represents seconds. So basically, if you just type in 30 for t into your calculator, I know it's a long polynomial, but if you just plug in that t or plug in 30 for t, that will tell you the distance after 30 seconds. So that's just a matter of plugging the number in because d is distance traveled, which is what you're looking for, and then it tells you specifically for 30 seconds. Now, I know there's a typo. It says x to the third instead of t to the third, but, it should be a t to the third there. Just plug in the 30 for all the t, and you should be good. All right, that's going to be it. Sorry the video was so long. I didn't want to make it that long, but it just had to be that way. So at least it was somewhat helpful. I'll see you guys in the next video. Bye.